Okay, so what we have done till now is the following. We learned data visualization, the first class. So we know if we see data plotted, we can interpret more or less. We saw sampling theory, important for doing surveys. Now, when you do a survey, what you're doing is an statistical analysis. For example, you see how many people reply this question, how many that, and on the whole population, you start to assign variables or values to those responses. That's an statistical distribution, really, what you are doing there. Then after we learn it, the memory doesn't fail, is basic statistics, distributions, the Buckingham theorems for dimension analysis, for finding expression, design of experiments, then a little bit of calculus. Once you have the expressions, for example, I have these expressions here, I can start to play with my calculus. I can find the derivative with respect to time of this quantity, derivative with respect to the demand, etc., applying the calculus rules. And if I want to extract more information, I can use linear algebra, use a matrix to collect the data and find the principal axis, which is the eigenvectors. Okay, great. Then now we close the cycle with estimation theory. Estimation theory is a complement of what we saw before about statistical distributions. Now, for these things, there are no magical formulas. Evidently, you have to go deep into this subsequently, but at least the idea of this course is that you have an idea which tools are available, which ones you decide to use. Now, there is a chance that if you are qualitative, you say, no, I'm not interested in using this and these tools. I will only use a few statistics, a few things. That's also okay. Statistics is not mathematics anyway. It's a little bit of data analysis and so on. Then, let me see this one. So estimation is basically finding values of unknown parameters. Usually we estimate some values. We have some estimators. For example, the estimation of the expectation value is the mean value. The variance has some estimations also. Then an estimator is unbiased if the expectation value of that estimator is the same value. Of course, if there is a bias, then that estimator, the expectation value is different to the value you usually expect. And this can happen because normally you don't know the value of the variable. You have to do some estimation. Now, there are some issues. For example, the variance. We need a quantity for estimating what is the variance. And this is the estimation of variance, like this one. Now, bias versus unbiased estimator. What is a biased estimator? I told you, is when the expectation value of a quantity gives you the same quantity. Now, if you have two quantities, one bias and the other unbiased, which one do you think you should select? Initially, the unbiased one. Unbiased means it doesn't deviate from the mean value. Do you remember the mean value? You remember that? When we saw distributions, there is an average. For example, what is the mean age in this class? I could tell your ages, this age plus this age plus this age plus this age. divided between the total students, and that gives me the average age. No? That's the expectation value of the age. For example, it's an estimator of the expectation value of the age. Okay. But sometimes these quantities are a bias. They have some bias, but in general, we prefer the one with a small variance, no? For obvious reasons. Small variance, you can trust more. You remember what is the variance? Let's find the distribution here. Let's put the distribution here. Distribution. Density of probability. What the mean value. And the variance was the deviation of the data with respect to the mean value. And of course, the closer, the shorter, the smaller the variance is, I can trust more in that quantity. No? Is the idea. This is an example where I don't think this example is so relevant because, but you can be convinced that if you calculate the expectation value of this, the expectation value of x is a random variable is mu, or y is 2 mu, and this is a function. C is a function of x and y. If you calculate expectation value of C, you find is mu, exactly the mean value. So this is an unbiased estimator. C is an unbiased estimator for mu. And if you calculate the variance, you can start to play. Well, here they do a little bit of calculus. And I found that there is a global minimum for the function. Well, of course, this quantity, well, this part is not so relevant. Just don't pay so much attention to this part. But you can find the minimum of this function. It happens at a equal 1/4. And then, of course, when you replace a equal here, you obtain the right value for C. No? You replace 1/4 here, and so on. Now, you can report estimates. Usually, the way to report estimates is you have the estimated value plus minus the standard deviation of the estimator. Somehow, the standard deviation is a measure of how much you deviate from the mean value, and we already know that. Usually, of course, the estimator from the variance is sigma squared itself, which we know how to calculate. We have seen that in the previous sessions. And for the mean value, usually this is the typical quantity. Well, no, it's not always the case, but this is usually the estimator we use. This is the estimator from the variance. These are unbiased estimators for the mean value and the variance. Then let's go for an example. X is the production at a department randomly selected day. We observe X1, X2, X3, X4, fine. Then you find unbiased estimator for mu, for the mean value and the variance. And then, of course, you start to calculate in the standard way, as you saw in the formula, and you will obtain 217 for mu and 36 for the variance. Now, the most important thing is the construction of confidence intervals. So the theory says that if you have an estimator for an unknown parameter, then you can construct a confidence interval in this way. The probability of the difference between the estimator and the unknown value should be smaller than equal to some quantity. And that's equal to 1 minus alpha. And usually we fix the confidence interval to be 95%. 95 is a standard way. I mean, there is no reason for that. It's simply that we trust a quantity if it can cover 95%. Right? Then, for example, you can have a quantity, the estimator, the quantity you observe is theta bar hat. It can be between theta minus d to theta plus d with a probability of 1 minus alpha. okay? So once you select one value of theta, that value of theta has a probability to 1 minus alpha to be between these two values. Let's put on the board better. Let's go to the board because I see face is a little bit lost. Estimator. Non-parameter. This is the parameter you want to estimate. Then there is a probability. What does it mean, this quantity? What is the meaning of this quantity here? Who can tell me here? The difference between the estimation and the real value of the variable. You are estimating, you are trying to guess. For example, I try to guess your age. I can try to guess your age. I can say 20. Yeah, 20 minus your age is this quantity here. It has to be smaller than equal to some number. And the probability that this is true is 1 minus alpha. And of course, we want that your age, your real age to be, we want to trust in my choice. We want to be sure that in 95% of probability that I am right. There is 95% of chances that I am right. And this is the confidence interval. So you fix alpha to be 0.05. With examples, you will see that. You will see the examples in a moment. So once you fix the confidence interval, you realize with the standard normal distribution that C has to be 1.96. Do you remember what is C in the standard normal distribution? Let's remember the standard normal distribution here. Standard normal distribution. It was this. It has 0 expectation value and variance equal 1. Do you remember? Sigma square equal 1. This is the standard normal distribution. And G of C, if I put C here, G of C was this area. Is the probability from minus infinity to whatever value C takes. In this case, 1.96. I can put C equal 1.96. That means that this remaining area is only 5%. Actually, 2.5%. 2.5 because there is a 2.5 there on the left by symmetry. So this defines my confidence interval. Then at the end, I confirm that my estimator, my good estimation is like this. Theta plus minus 1.96 standard deviation. This quantity here has 95% chances of covering theta, a variable which I don't have any idea. I don't have any idea about your age, but I want to construct an interval where I am 95% sure that your age is between those two values, a maximum value and minimum value. I can construct an interval. Your age will be between 30 to 20, for example. And all of you are younger than 30 for sure. 30 to 20. And I want to be 95% sure that your age is between those two values. That's an example. Pay attention that I understand that this is probably the most difficult part of probability theory. I think in this part, many people struggle. So, but remember, revise the Gaussian distribution, the normal distribution is very important. That's why we revised that distribution last time. This is a standard, C1, and this is the picture. 95% is here between 1.96 minus 1.96. This is the normal Gaussian distribution. Now, this is an example. This example will clarify everything to you right now. All the doubts are solved with this example. So look at the board for a moment. Theta is unbiased, approximately normal, and sigma theta is 25. This is the standard deviation for a normal distribution, not the standard normal distribution. Remember that the normal distribution can be shifted. What does it mean shifted? Shifted means, I'm asking myself, if I move this curve to somewhere else, I can have a different mean value and different variance. Okay? So anyway, sigma is 25. Find 95% confidence interval when we have observed theta 210. So 210 is just a guess. It's just your guess. You say, this is my guess. I draw this by myself. Then, of course, the confidence interval will be this theta plus minus 1.96, which I recalculate times sigma. And sigma is already given here. And then 210 minus 1.96 times 25 is 161. So it means you do it first with minus and then with plus. With minus, you obtain 161, which is the lowest limit. And with plus, you obtain 259. So this is the maximum value and this is the minimum value. So I have 95% confidence interval that my guess is here between these two values. Okay? I mean, sorry, I used the wrong words. I say my guess. Now, this is my guess. There is 95% of confidence that the real value, which I don't know, is inside between these two values. The real value. What is the real value? I don't know. Okay? Maybe I am wrong, maybe I am right, but the statistics say that I have 95% of chances to be right. Yeah. This is more, this is estimation. Well, for confidence intervals, we need to calculate expectation values. You have variances, and you have if you have the 95% confidence interval, is defined in this way: mean value for some random variables with that expectation value. You have the mean value plus minus 1.96, and this is representations of the variance actually, of the sigma we saw before. It's a way to estimate the sigma. Now, there are cases where we don't have the normal distributions are accurate when there is a huge amount of observations. But when the observations are little, not so many, you use something called t distributions, which has an additional parameter. We have, besides the expectation value and the variance, you have t. This t is a parameter which has to be calculated. N is the number of observations. This is just an example. For example, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 observations. So the new you saw before is 8. And then you can calculate intervals of confidence in the same way as before. This part I will not emphasize so much because we seldom use t distributions, but this example I will ask you to revise, please, on the slides. Subsequently, any question? Look at the confidence interval here. Okay? Why did they do this? Because they had to compare between the ordinary distribution to the standard distribution, etc. But you will realize that it's not that complicated. after a while. And this is the generalization when you use the t-test. T-test is only for a small amount of data. It's more or less similar to. Now let's go to the most important topic today. The most important topic today, we still have time, is hypothesis testing. Sometimes in your research, you want to I want to see if I am sharing the right screen. Let me see. Oh, okay. Well, sometimes you have a hypothesis in your research. Then you have to create a hypothesis and a disjoint hypothesis. For example, think about something, tell me something, some hypothesis you have. Do you have any hypothesis in your research? Any word? For example, if somebody throw me water, I get wet. Hypothesis. Could be a hypothesis. And the disjoint hypothesis, no, I keep dry. That's an example, no? Naive example. Of course, we will see more serious example, but this is a way. Then you have a null hypothesis. Your null hypothesis could be anything. Could be what I just mentioned now. Or for example, you flip a coin. Null hypothesis could be the probability of, we will see that example later, probability of tails or head is 1/2. This is my hypothesis. And the disjoint hypothesis, the other, is that no, it's not 1/2, it's something different. Hypothesis, you are wearing black dress today. I have not seen you, I say you dress black today. Null hypothesis. The complementary hypothesis is what? You are not dressing black. Is what complements, no? Is completely disjoint. So the null hypothesis, of course, if the null hypothesis is found to be wrong, the alternative hypothesis is correct. If you cannot conclude a null hypothesis is wrong, we cannot conclude anything. All hypothesis tests have a static test and rejection. This is just words. It's not that important. A static test is just a random variable. Of course, we have a rejection region. We will explain later why is that. If there is sufficient evidence to reject the null hypothesis. Of course, we are never 100% sure about our conclusions, but we try our best with the amount of information we have. Statistics is matter of information. More information we have, the better you can conclude. So there's always a chance that we reject a true null hypothesis, and this is called false positive or type 1 error. There's also false negative, or type 2 error when the test fails to reject a false null hypothesis. So, I mean, for hypothesis, let's summarize a little bit. You need a null hypothesis, which we signify by the symbol H0. You need an alternative hypothesis, which we signify by the symbol H capital A. A random variable, they call it a static test, but this is just a random variable. And we need a rejection region. So it's where you reject the null hypothesis if the test falls in the rejection region. Then, for example, this is the distribution. This is the rejection region, this one. By convention, 5%, the same 5% you saw before. Rejection. So let's go for examples. First example, how is the time? Still 15 minutes, right? Okay. Example, this example is in the textbook actually. I shared with you the textbook before. Statistics, no? Okay, I will share with you anyway. I will post in my USJ. But that textbook has mistakes, errors, typos, typos. So if you don't understand, you can't believe that something is right and it's not right. Better I will share another book. Okay. But anyway, it's important to go to a book of statistics and try to take a look at this. This is assume that stock price K of a stock in a collection of some particular company is a random variable which is normally distributed with mean and variance. The mean and variance are unknown. So saying zero here is wrong, for example. Hypothesis, null hypothesis. The parameters in the normal distribution are 100, 100. Mean value, variance. This is my null hypothesis. I want to verify if it's wrong or right. The complementary hypothesis, or whatever you want to call it, is just a name, is that when mu is different to 100 and sigma square is different to 100. Because it's everything else, all the other possibilities. Of course, my test will use the random variable they put, K. And then they ask you to reject the null hypothesis if your variable is inferior to 80.3 or larger than 119.7. Those values, of course, those come from the 1.96 you saw before by convention. But then, of course, we want to see if we can reject this quantity. Okay? Then I calculate the probability of this t to be inferior to this, and the probability of this t to be larger than this. And of course, this is just a convention. Now you convert this from the normal distribution to the standard normal distribution. That's why you see this conversion. Of course, I'm sure that some software can help you in that. We will go to that on Thursday. But for the moment here, this 80.3 is this 80.3 minus 100. 100 is the mean value. Root square 100 is the root square of this guy. Plus the probability of t larger than this is 1 minus the probability of 80.3. So that's why you repeat, being smaller than 80.3. So that's why you get this. So at the end, you obtain these quantities. This is just calculation, 1.87, 1.87. At the end, you obtain 5%. These intermediate steps, don't worry so much. You will understand that later. But if you remember the previous classes, this is the conversion to the standard normal distribution, this part. And this is G of Z, because this at the end is minus 1.97. Minus 1.97. I thought it's 96, but anyway, I don't know why they put 97 and 1.96. This is 2.5% here. And this is 2.5% here. Okay. You obtain 5%. When you obtain the probability, of course, you have to conclude. The probability is that the values are smaller than this or larger than this is 5%. So I want you to think if I should reject the null hypothesis or not. Later, I will share the example with you and you have to think by yourself. you reject or not the null hypothesis here. Is to guarantee that you are paying attention. Now, for the idea, the general idea, you have a hypothesis, you have a complementary hypothesis, you have a random variable, and you have to create a criteria of rejection of the null hypothesis. And then you calculate the probability of the probability of being rejected for the null hypothesis. And the idea is that should be very small for me to accept the null hypothesis. If it's too big, I have to reject. So think for a while. Now let's go to the examples 9.3 and 9.4 from the textbook. I'll go to the textbook, Springer. Nine point three is about tossing a coin. Should be this one. Wait. Oh, wait, not yet. Because I have to put the textbook in the other side, right? I have to put it here. This example, I mean, these things are with examples. If you see the examples, I am sure you will catch it. Because obviously the theory, especially in statistics, they use a language. Their English is not so friendly, I must say. So I understand your faces. Let's go to this example. Very easy. Let me check that I am sharing the right screen. I will remove this. Okay, it's correct. Over the shoulder. Great. Let's go to this hypothesis test. We are flipping coins with a friend. I don't know if you flip coins with a friend, but anyway. After losing, of course, you are losing 50 times in a row, you have the feeling that something is wrong. Your friend is manipulating the game. It can happen with dice when you're playing dice or I don't know, when you are gambling, the roulette, whatever. Then you want to examine in detail if the coin is biased. Let's say the coin is more into head or more into tail or whatever it is. Then you make a null hypothesis. Your hypothesis is the probability of heads is 1/2. And the complementary hypothesis, the probability of heads is larger than 1/2. This is disjoint to this, but of course it doesn't cover anything. It's not symmetrical. Then, of course, you create a random variable. Your test involves a random variable. You assign 1 to the heads. When you get a head, you write 1. When you get tail, you put 0. That's a random variable. 1, 0. You know the expectation value is just P. The expectation value of this experiment is just P, which is 1/2. The variance is given by this. Then the static test, they use the mean value. Of course, they flip the coin 1,000 times, and they divide by 1,000 here. And then this is the result. Let me see. I think I skipped something. Actually, I'm in the same page. Then this is the expectation value. This is the variance. 1,000, you have to divide because it's 1,000 times. Then, of course, the null hypothesis say that the probability is 1/2. So if you see too many heads, you should reject, no? But there must be a limit after which you reject. I mean, you tolerate a little bit of bias. Let's say that the probability is 1/2. It's not 0.5, but 0.51 of getting head still is okay for you, no? 0.52 is still okay. So in which moment I start to reject? 0.50 what? 0.6, 0.7? I need to estimate that quantity. Then these guys, they use the standard ways to use 5% of significant level. So it means you design a test such that the probability of false positive is 5%. So the probability of rejection, let's say. Of course, your hypothesis is 1/2. The probability of ending up with a rejection is 5%. So you impose this condition. 0.05 is 5%, right? Everybody knows that. This is the probability that the P, the estimator, the estimation of the probability is larger than equal to some limit, has to be 5% or inferior. We know that there's something called central limit theorem, but you don't care. This is a normal distribution because it's 1,000 attempts. When there are so many attempts, it's normal distribution. Right. Then, of course, this is just carpinteria, we say in Spanish. You are the carpenter. You just use the equations here. The probability of P is larger than some limit is 1 minus the probability of being inferior to that limit. Because the sum of probability is equal to 1. Let's put it this way. Let me paint again the normal distribution for you to see why this is the case. You have tan, tan, tan. Let's put this C. C. And then you have some limit. Let's put the limit here. And you want to calculate the probability of to be smaller than the probability of P larger, sorry, the opposite. P larger than the limit, so it means this side, plus the probability of P smaller than the limit, so this other side is equal 1. And that's why you have, when you solve for this guy here, if you solve for this is 1 minus the other quantity. So that's why you have the 1 minus the other quantity. But this 1 minus this is 1 minus G. G is the function, the function we find in the tables, remember, for the normal distribution. And you have to do the conversion because P is an arbitrary number. You have to convert to the standard normal distribution, which is the value minus the expectation value. The expectation value is P divided by the variance. The variance, no, the standard deviation, actually. Here. Both the mean value and the standard deviation are functions of P. And you know that P is 0.5 because this is your hypothesis, no? 0.5. Then you replace. Then you have to put 0.95 for GCG of C because you want to accomplish this condition, 0.05, 5%. Then you obtain C is 1.6. You solve for this, and then you obtain that the limit for rejection is 0.526. It means that when I flip the coins 1,000 times, and I found heads with chances larger, equal or larger than this, I should reject the hypothesis of 1/2. I should reject that hypothesis. It means that my coin is biased to one value, to head or to tail. In this case, I think it's head, right? I think they mentioned head. Yeah, heads. Of course, they are concerned about the heads. Excellent. So, I mean, it's an exercise of logic, of course. And now it means You reject the null hypothesis. What was the null hypothesis? Who remembers? Null hypothesis was the probability of getting head is 1/2. That's one my hypothesis. In your research could be the probability of getting what's your research about? Yeah, but what's the topic? Efficiency of institution, right? Yeah, I remember. Then your hypothesis is, well, no, I don't know if it's correct to say that. There's no corruption. Now, something like that. Let's assume there's no corruption. Your null hypothesis. And then you create an alternative test. Let's put here. I mean, learn the concepts at least. Your null hypothesis, we say no corruption. And the complementary hypothesis is there is corruption, or vice versa. You have one has to be excluded by the other. No? And then you can make some statistics, some numbers, some data, and make some tests. This is more or less the idea. And now the details now it's not even that important at this point that you know how to do the whole calculation. But it's important now, and this is the trick of quantitative people, because even myself, when I studied for first time something, when I was bachelor and you study for first time, some theories you say, what's that? Oh my God. It happens to everybody. But at least the important is you try to understand the concept behind, you have to understand how to use it, etc. But I mean, the exact calculation is after you at home, you start to see yourself, the details and so on. Because of course, in one session, you will not understand all these things. But then you have some tests. You have to design your random variable. What's the random variable indicating there's an index of corruption? There must be maybe index of corruption or index of efficiency of institution. For example, you can make a null hypothesis. These institutions are inefficient. Then you have to mark what does it mean inefficient in the sense of variables. There must be a random variable or some index indicating whether an institution is efficient or not. And the other hypothesis is the opposite. All the institutions are efficient in Macau. Or transportation. One null hypothesis could be the transportation in Macau is efficient. And the alternative hypothesis is the transportation in Macau, I say efficient or inefficient? What did I say? Okay. The alternative would be the opposite, inefficient. It was transportation, and I think it's the second will be the winner. In that case, of course, I will find a rejection of my null hypothesis. The rejection, me saying that the transportation in Macau is efficient is false, absolutely false. The transportation in Macau is no, don't misunderstand. It's a nice city, it's very rich, it has money, but the transportation is bad, and you must confess that. I mean, everybody will agree that it takes eternal sometimes for go from one point to the other. So you can create hypotheses, but you need some random variable measuring for measuring that hypothesis. And that random variable I cannot give to you. That will have to be found by you or created by you. Created in the way how we learned before. We can create variables from qualitative data. Qualitative data means characteristics, qualities of the institutions can be quantified. Okay? So in this case, of course, these guys found that if you obtain 526 heads or more, then your null hypothesis is false. You have to reject it. Now, the example 9.4 occurs. Let's go to break now. It's 8:33, no? 8:33. So we can take a break here. Take a break.